Okay, my name is Tristan Nguyen. This is my second year managing this portfolio, which is about information science and fusion. Information science is basically computation on various data structure, simply as that. And what is fusion? In fusion, you want to assimilate tidbits of information from various sources, taking also into account of observed data, and to be able to synthesize new knowledge or to be able to make inference. So as simple as that. So what's the difficulty? Well, we need a great deal of science to take that boundary to separate between humans' ability and machines' ability to process information close to the human side. Okay? In other words, you want to have smarter things that facilitate or that help us to process information. And that is still a very difficult subject because we human, we think at higher level. And right now, if you look at, for example, the semantic technology, which is basically grounded on first-order logic, and you know the humans think far beyond first-order logic. So we have to do a lot of thinking to reduce it, whatever we have in our mind, to first-order logic and put into software for it to work. And sometimes it's very difficult for me to understand another programmer, you know, if I am a programmer, to understand what the other person has had in mind to begin with. Okay, so it's quite a challenge. So we still have a long way to go. So those are the two challenges that I put down in a different way. So right now my portfolio, my portfolio consists, I basically cluster the projects into three different areas. This is the higher level computation or higher level information processing. That involves data analysis and information fusion. And then in the middle, which is more algorithmic driven. And at the bottom row here, I have a number of projects that deal with sensors, radars, but fusion of sensors and radar to detect anomalies in network. Okay. So in terms of dollar amount, the orange wedge here of the pie denotes the university funding. And the red part here stands for the lab task, LRIR. And I have two STTR, which are coded in green. And one of my colleagues at AFOSR RY, Vince Velton, is managing one of the two STTR efforts. And then I have one MURI project that I am going to talk about that a little bit later. I do think that my program will contribute to these four technologies. These are the technology, not science. And these four technology, I think, are critical to enable Air Force missions. These four Air Force missions: autonomy, cyber domain, SSA, and ISR. Of course, my program is not the only program that contributes to these four technology. Okay, I'm not claiming that my program solely supports that. In terms of collaboration and transitions, I want to begin with autonomy. I have recently begun to work with Dr. Morley Stone and Fariba Farouk in this area of autonomy because Dr. Morley Stone has taken over the leadership of the initiative on autonomy that was initiated within the OSD. And I'm helping out Vince Velton and his group to take charge of the MSEE program at DARPA. By the way, Vince's group is the agent for this program. So I have been helping them out. I have closely collaborated with my ARO's PMs over the year, and two of them are here today. The first project, or the first MURI topic, is about modeling and understanding rare phenomena. Okay, but here in terms of heavy tail statistics. Harry Chang is the PM for the MURI topic, And the other topic is more on the line of bioinformatics, that you can say. Okay, a little bit of experimentation regarding microorganisms and how you can take various types of data that you got out of experiment and model the microorganism in light of the environment. So Virginia Pasur is a PM for this MURI topic. And then in terms of transition, I have 2 little projects that got transitioned out of AFOSR. Okay, future direction. I want to de-emphasize sensor radars and communication network because this area is being handled by my colleague John Shogren and Bob Bonneau. So I am going to start to de-emphasize this area and put resources into what I call higher level information and computation, which I am going to say a little bit more in the next slide. Okay, and these are the rationales for reshuffling my resources. First of all, there are emerging developments in what I call higher level information and computation. And I think that it's an area that the Air Force has to keep a close eye to, besides sensor. Okay, so now I talk about high-level information and computation. First, I will talk about information processing at high level. What does that mean? Well, if you want to process information at a higher level, first you have to have very rich data structures, okay? So that you can encode various data types, A and B. You have to be able to encode abstract knowledge representation, okay? So you need to have very rich data structures, okay? Now, but if you just have this, then all you're doing is just characterization of information, okay? Just representing information. So you do need some sort of computational framework so that you can manipulate these structures or compose these structures, okay? But we don't want humans to do that, right? You want to be able to specify how you can construct the structure or compute these structures. So you have to have a programming language to specify how computation can be done. And more importantly, you need to have some logical construct at higher level, okay? So now, recently, now let me talk about these 3 different research communities. And recently, there's been a converging, there's converging movement between these 3 communities, okay, when they look at these 4 different areas of research. Let me first describe this area, cognitive psychology, and how a subset of researchers in this area approach the problem of reverse engineering cognition in terms of these 4 structures, these 4 areas. So they think that abstract knowledge can be represented by data structure, abstract data structures, okay? But on top of that, so that's the lowest level. On top of that, if you want to describe mental representation, okay, or you want to describe knowledge in real-world situation as opposed to just abstract knowledge, then you can use probabilistic generative models that are defined on top of these data structure. Okay? Well, to be able to construct those generative models, they actually rely on programming language, a functional programming language to be able to do that. Okay? And eventually they want to include logic in it. Okay, so there you have very close connection between these four areas and cognitive psychology. Okay, so and recently in these two communities of research, there is a thing called high dimensional type. Okay, that came out of programming language, particularly generic programming language. What it is you want to be able to program on arbitrary data structure, and you want to be able to lift specific computation or algorithm that is designed on specific data structure to a more general abstract operation. Very much in the same way that cognitive psychologists describe in terms of generalization when it comes to learning. Okay? In terms of constructive mathematics, well, these two areas are historically known to be connected. Okay? But no explicit, but the link is quite tenuous up until this point. So in terms of constructive mathematics, there's a notion of homotopy type, which turned out to be equivalent to high-dimensional type theory here. And in fact, there is an ongoing program at Institute of Advanced Study, 2012 and 2013, that studies a new foundations of mathematics, completely new foundation of mathematics. It's called Univalent Foundations of Mathematics. Okay, so they are clearly connected, these three areas. Now let me highlight some research project. I will first describe MURI project and then my core portfolio. The reason I describe the MURI project first because it cuts across all the sub-areas of my portfolio. So my predecessor initiated this topic. Doug Cochran was my predecessor. So the goal here, let me give you an intuition of what's going on in this MURI topic. If you have several moving platforms, okay, flying around or moving around, you want to be able to collect information that meets certain objectives. So how are you going to control your moving platforms to achieve what you want to do? Well, of course, there are physical states, and then there's a notion of information or informational states, okay, that describe your goal, and you're getting information from sensing as well. So basically, you got the coupling of physical state, information states, and sensing. Okay, so it's challenging. This MURI topic is related to two MURI topics that are managed by Lee Dai, my colleague at ARO. I have closely worked with him over the years. And I will explain a little bit later on this project, LRIR project, and how it is related to this MURI topic. Okay? Okay, so the MURI topic has three different research area. We will focus on these three sub-areas: control of information, information sensing, and think of this like the space of all possible formation. Okay. Okay, so I will first describe the space of all possible formation. Here you got 5 objects. Okay, quadrocopters, you can think of like quadrocopters. So they change formation. So we want to be able to describe all possible formations, because remember that these things are collecting information for a certain purpose, right? So you want to study, for example, your objective on the space here, that abstract space here of all possible formation. The space is called space of configurations in general. Okay. However, it's very difficult to put your hand on the space here because it's so large. So if you look at these objects here, you see that how they got clustered. Okay, obviously how they're clustered. So if you can think of a clustering scheme, then you can describe this as simple as that. Okay. Now you can do computation more quickly on this space here. That's the gist of the ideas. And the preprint is being circulated right now. Okay. All right, so once you have space of configuration, the next thing you want to do is to be able to do planning, okay, to achieve certain objective on the space of configuration, right? So in this project, the PIs are studying, this is test cases, okay, for control theory in terms of differential game. Here is capture of the flag game or lion and man game, okay, that are described in terms of Hamilton-Jacobi equation with Isaac's conditions. Okay, the strategy are obtained by solving this equation, and the evolution of the strategy are also described by the solution of this equation with respect to some boundary conditions. Okay, and you see that this simple game here can get very complex very quickly, okay, if you have multiple defenders, or you can have multiple players and then you can have obstacles, okay? So it can get very complex very quickly. All right, now it comes to sensing. So your object of flying, okay? So here we are assuming that sensing can be represented in terms of probability distributions, okay? And this family of distribution vary with respect to this parameter that describe the space of formation S here, configuration space, okay? So it's well known that if you take the Fisher information, then this is what you get. So, but this, you see the indices I and J, it turns out that you can view this as a matrix. Okay? Or in fact, it is a metric. It's well known. Nothing new here. This is information geometry. Okay? But the new thing here is now we have to study all possible I, this matrix I here, or the space of all possible Riemannian metrics. Okay? And it turns out to be an infinite dimensional Riemannian manifold. So that's part of a study that this team here is studying. By the way, the PIs are not funded by the MURI funding, but they're funded by my core program. Okay, so I will go ahead and describe my core program. So again, I remind you the 3 areas in my core program. And these are some projects that I am going to talk about. Of course, there's no preference here. Just the continuous flow of information from the MURI project to this LRIR, and then eventually down the column. Okay? All right. So this project is about layered sensing. It's a concept that was originated from the sensor directory. It's a very influential concept. So what it is you are taking all possible information there are from sensor platforms and humans, and somehow you want to be able to generate situation awareness, okay, with certain requirements. Okay? So it's very simple. Here I have just one line description of what it is. It's I think a 40+ page document. But it's very complex because if you look at here, there's so many types of information. And if you see the keyword here, layered. So you have to be able to understand that in terms of layered and how they are coupled, how they are related. So it's a difficult modeling problem. So the PI in this case is a NRC postdoc, Jared Culberson, working under the supervision of Vince Velton, okay, in the sensor directorate. So the technical method that he's using here is category theory of probability spaces. Okay. By the way, the Air Force funded Southern McLean, I think as early as the 50s and early 60s on category theory. And he went on and got the National Medal of Science in 1989. Let me backtrack it. Co-funded. Okay, Air Force, co-funded. Okay, so why do we need category theory? Because it's a perfect machinery to describe things at certain level of abstraction, put it that way. Okay, so what it is you're studying the totality of these spaces, probability spaces, and their relationship. That's all there is to it. Okay, how is this related to the MURI topic? Well, remember the three sub-areas that I outlined: configuration spaces, information sensing, and differential game theory, right? Well, it turns out that this is exactly that. Okay? Hierarchical clustering, remember the formation? Hierarchical clustering, if you want to have consistencies in that hierarchical clustering scheme, you have to invoke category theory. Okay? And if you want to study strategies in general, strategy are nothing but mapping between probability spaces. Okay? And finally, the notion of information geometry was actually co-discovered by Chensov in the early 80s, late 70s and early 80s in terms of category theory. Okay, so you do have a strong link between this LRIR task and a MURI topic. Okay, the next project is being researched by Gunnar Carlson at Stanford University. Here he studied data fusion using topological methods. So you have to assume that your data can be our point cloud data sets. Okay? So point cloud data set, you hope that you can have some notion of shapes. So you want to study point cloud data set by studying the shapes, okay, of that set. Okay, so studying shapes, there are several ways of doing that. If you want to have robustness, then you invoke topology. Okay, so this is one way of tackling the problem. And here are doing this. And in terms of fusion, by the way, in terms of fusion, data fusion by topology reduces to studying, here we go, mapping between topological spaces. Okay. This technique is becoming increasingly popular. Microsoft Research has funded topological quantum computation in the late late 90s, and then you're seeing, computation of this type of, computation of electromagnetic equations, certain EM equations using topological methods. Okay, and electromagnetic cloaking. Well, this is hidden in there. Okay. All right. So the second method that we fund here is by embedding and matching. Classically, okay. So you have two different modalities here: zeta 1, zeta sub 0, and zeta 1, and both modalities are sensing the same phenomenon. Okay. So you want to be able to somehow put these two different modalities into a third space. Okay, so from which you can match points, okay, so that you can classify. Okay, so this is an example of data fusion for pattern classification. Okay, so the old method, in the old way, you just work individually on either this or that. Okay, so you start out with that, and you use this matrix here, delta sub 0, delta 1, which describe the similarities within each modality. You embed it in there, but okay, so that's what. So what it can do is it can preserve the similarities, but it doesn't tell you anything about cross modalities. Okay, so the new way is to construct additional submatrices W, which describe the similarities between data points across modalities. Okay, so it takes some skill here to build this matrix W. Okay, so assuming that you can do that, then you can use the standard multi-dimensional MDS, multi-dimensional scaling methods to embed this in this space here. Okay, and then you can do classification. So this is a like a test case, the PI work on Wikipedia documents, English and French, describing the same topic. Okay, and the green curve here describe this method compared to individually the other two methods, that and that. And you have an improvement in terms of classification. Okay, the next project is similar, is along the line of the previous project. That is manifold embedding and target and object identification or classification. The PIs are in RW, so what they want to be able to do is to detect various targets, okay, whose data are collected by different platforms with different computational capabilities and different sensor capabilities. So you have a mismatch between sensing modalities and your computational capabilities. Okay, so whenever there are challenges, there are opportunities. So these are the things that they are looking at. So here you have LiDAR data, and here you have long-range LWIR data. Okay, these are synthetic data, not real data. Okay, and so far this is what they have done. They constructed feature vectors and reduced to 2 dimensions to see if you actually lose, how much information you have lost. And the picture on the right show you 2 different approaches. Their approach versus a classical approach using PCA. And you see that here you get nice separation between data points. So you can clearly pinpoint, this is one object, and perhaps this is another. These data points describe another type of object, and so is that. Okay, so you want to be able to separate the classes. Okay, it's much harder here. We can separate that, but machine can't. It's harder. Okay. The next project is performed by David Bly. He is being funded by several agencies from Princeton University. He giving us a new way to do regression. Okay, and let me quickly describe why is it new, because typically you can, what is regression? You want to be able to fit these data points. Simple as that. The best way you can. Okay, so typically people use either that or generalized linear models or Dirichlet process mixture, okay, to do regression on data points. Well, each one has its own disadvantage. For example, here we go, generalized linear models. Of course, here you're looking at, you see the keyword here, linear models. Okay, so you see the restriction right away. On the other hand, this is non-parametric procedure, okay, which tend to give you lots of freedom, which means that you overfit your data. So you can overfit your data or underfit the data if you just use one of the two. So here's a framework in which you can combine both. So what's going on is if you look at this picture locally, just look at locally. Okay, locally, what the method does is locally it's just a mixture of linear models. But the problem is, how many mixture components do I need? Okay, that is when I need to bring this Dirichlet process into account. Okay, so it automatically tune to tell me how many components I need. I don't have to do it in an ad hoc fashion. Okay, so if I have enough training data, then I can do that. And I like this approach because you can actually tackle categorical as well as numerical data simultaneously. The next two projects focus on high-dimensional data. Typically, you really want to ask the question how much information you need to do certain thing. Okay, it's important, but it's very vague, but important question. Okay, so this project and the next one attempt to answer that. Okay, so in high dimension, we're looking at high-dimensional data, but with very few data points. So that is a new trend in data analysis. as opposed to the classical framework where you fix a dimension and then you have a bunch of data points, and then you find theory, asymptotic theory that describe how your model behave when the number of sample goes to infinity. Okay? Here you're restricted to certain number of sample, most of the time much less than the dimension. So that is a difficulty. Of course you can't do that without further assumptions. Okay? So in this project, the PI assumed certain form of function so that he can recover it or estimate that within a prescribed error. Okay? He also gives you a constructive way to find this algorithm. And here you can see it. He applied it to two-dimensional case, okay? Fitting LiDAR data. And this is not trivial because when you deal with LiDAR, you have lots of missing data points, okay? Unlike computer graphics, where you can assume that you have great fidelity. So you can use a lot of fancy technique. Here you can't. It's much harder. A lot of missing. But you can see that, see the poles here, very thin object. Okay, this is what you see from LiDAR data. Look at how he could get it here, the thin pole. Okay, it also allowed you to. He also found a constructed way to code and decode. Okay, so it's not just approximation, but code and decode. Okay, along the same theme of the previous project, here Montanari, a young researcher at Stanford University, this is a recent result, which was announced in November or December of last year. Okay, so compressed sensing is a very popular subject. Recently, there have been surprising applications of compressed sensing. For example, in the area of prediction of energy of biomolecular interaction, okay? And different types of imaging, the fluorescent imaging, compressed sensing. So it's still a long way, okay? So there are a lot of things need to be done in this area. So what is new here? Well, what it is doing here is in this framework, compressed sensing, A is a matrix. Okay, it's a measurement matrix. It could be hardware, software, or just a measurement matrix. And you're measuring the unknown x here, and you want to reconstruct that. Okay, so what you're observing is y, but you want to find x. You want to go back and reconstruct x. Okay, but most of the time you can't, because this matrix is a fat one. It's short. Okay, the number of columns is much more than the number of rows. Okay, so you have to make further assumption. Unlike the standard compressed sensing formulation, where you need to have sparsity of x. Okay, here you don't need to, but you need some sort of assumption on the distribution. That is, x is generated by some particular form of distribution. Okay, and it turns out that they came up with a dynamic scheme that allow you to reconstruct x much faster, okay, with theoretical guarantee. So this is the first time you can do it iteratively and get very accurate performance. Okay. And this final project, the final project is about sensor fusion. My colleague John Sjogren is going to talk more about sensor fusion, I think in next day or two. So sensor fusion, you're fusing data, but now at a sensor level. So most of the time, you just focus on the signal intensity from, say, two different sensors. Okay. Traditionally, people use the statistical estimation theory that people have used over the years in radar. So that still persists, okay, in this domain of sensor fusion. The problem or the challenge here is you can probably compute or approximate probability distribution from one sensor. Okay, you can do the same for a second sensor. But to be able to detect within the framework of statistical estimation and detection, you have to have the joint probability density function. Okay? So that you can set threshold and say if my joint probability is bigger than threshold, then there is an anomaly. Okay? So, but most of the time, we don't know how to compute that. There's no statistical theory that allows you to construct that. Okay? In this example, let me illustrate first of all what's going on here. So these are the data points. Okay? You assume that in high dimension, x of 1 to x of n plus m. So the PI used the last group from n sub n plus 1 to n plus m to approximate, to define statistical estimator for the density distribution here, f hat. Okay. Once you derive that, then you construct another statistical estimator for the entropy. Okay, using the first n samples. Okay, and then he derived a Gaussian limit behavior, which is good because it gives you a methodical way to determine the threshold based on the false alarm rate. And here's an example that he illustrates. Of course, here in this particular example, I think here there are 14 sensors that send people walking into a room. Okay, so the data points are not IAD, so they don't follow this hypothesis. But nevertheless, he showed that the result is decent enough that allow you to get some gain here, okay, in detection. So this is a summary of my talk. My core program consists of 3 sub-areas, and I want to put a little bit more investment in higher level information and high level information and fusion, because there's still a long way to go. I think that's a very challenging area. Thank you, and I would like to thank Dr. Hussey, who has helped me organize some of the ideas in here, and my colleague, former colleague Jun Jiang, who is not here today. He helped me to understand some of the programming, how we describe cognitive processes in terms of programming language and programming. Thank you.